Good evening, everyone. My name is Prarthi Kothari, your host for the day, and it is my privilege to introduce our distinguished speaker, Mr. Mridul Sharma. Mr. Sharma is a dedicated biotechnologist currently serving as a junior research fellow at the prestigious Indian Institute of Technology, Delhi. He holds a strong academic background in biotechnology with advanced training and research experience that spans both academic and applied domains. Mr. Sharma's research contributions reflect a commitment to scientific rigor and innovation, and he has actively participated in projects addressing critical challenges in biotechnology and life sciences. His passion for research and continuous learning marks him as a rising talent in the field of biotechnology. So please join me in welcoming Mr. Mridul Sharma, sir.
Thank you, Prati. I'm audible.
Yes, sir, you are.
Can I start?
Sure, sir.
Wait a minute. Let me share my screen. Is my screen visible?
Yes, sir.
Okay, let's start. Today's I'm not about giving a lecture, just giving you a short brief on what we are doing, how we are doing, and why we are doing it. As Prati said, I'm a junior research fellow in IIT Delhi. My main work is in upstream bioprocess. That's where we produce biotherapeutics, protein, or even some vaccines. Okay, so as all of you are a biologist, you also know what is biotherapeutics. As we know, the biotherapeutics are the biologics derived from the medical products or derived from the living organisms, but these are not produced in the these are made outside of from the living organisms. Either we can make using chemicals, drugs, or we can make via recombinant proteins. Basically, the biotherapeutics are produced via different methods of biotechnologies. The main method we know as small bio, the molecular biology. In biotherapeutics, we generally engineered cells like a mammalian cell, bacterial cell, or yeast cell, which produce protein or vaccine or even a monoclonal antibody, fragment of antibodies via bioreactor under using slice conditions. These biotherapeutics can be monoclonal antibodies, recombinant proteins, vaccines, either used in cell or gene therapies, or can treat a hormone disorder, many other things. The slide you're seeing, monoclonal antibodies are lab-produced protein designed to limit the immune system ability to recognize and target specific molecules, such as antigen or cancer cells. These monoclonal antibodies can be produced by mammalian cells outside living organism bodies, but these are the typical things which can we do in a biotechnologist. As a biotechnologist, I would say that you often hear about something called CAR T cells therapy. That's immunotherapy, which we use in cancer therapy or cell or gene therapies. Such antigens can maybe a Fab molecule or a MAPS, which can bind either to your immune systems, can mimic with response to a specific antigen or antibody. Second is the common proteins, as you are well aware of recombinant proteins. There are a wide variety of recombinant proteins or recombinant organisms on the market. We use that recombinant organisms, which they can inherit the desired gene of our product. That's the main idea. That's the main ideology. We use generally bacteria or mammalian cell. Why we are using bacteria or mammalian cell? Because bacteria, as you know, their doubling time is very fast. Just example of E. coli, the doubling time of E. coli is 20 minutes. That's why we get the result earlier than before. As well as in research and development, we need to develop a method. That's why we need a result which is a fast result to check the quality of a product or the quality of a product. Including vaccines. Before uh, jump jump to the large scale of productions, vaccines can be developed. Vaccine can be developed in a small scale to check the activities, either it is working or not. That's where we come the bioethics or the biotechnologist. Wait a minute. I think my screen is. Wait a minute. Okay. Sorry for the inconvenience. These are the applications of biotherapeutics. We can use monoclonal antibody for cancer therapies, vaccine, or the hormonal disorder. And the hormonal disorder I'm talking about, like someone is suffering from insulin or thalassemia. Either one has a growth factor disorder, which can be treated via hormone which are produced outside the body. Let's jump the main stream or the main work I am doing is upstream bioprocess. Upstream bioprocess is a main stage that involves many steps. Preparing, designing a vector clone that produce your desired protein or MABs or a recombinant protein, which will serve many therapeutic effect or biological effects. The first stage of these biotherapeutics to be designed. Either you don't design a biotherapeutic protein, they don't work. If you have a gene of interest of a desired protein, just for example, I said insulin. You know insulin in a world stage, there are many insulin disorders. Many of you know that someone in your family or someone your known relative may have suffering from diabetes. So insulin is for those insulin need daily. For that we can say we cut off the gene of interest. We have the desired gene, that is insulin gene. We are inserted into the viable cells. The cell I am talking about, like E. coli. We inserted the gene of insulin into E. coli. Then we make E. coli to produce the insulin. That's where the upstream bioprocess enter. The upstream bioprocess make that happen. That we make E. coli to inserted that gene of interest. We make E. coli to produce that protein. Either it is microbial culture, either it is mammalian culture. Even if it is a small scale, that is 1 ml to several lakhs of liter of culture. The culture amount is not directly proportional to the amount of protein produced in a E. coli. It can be varied. Let's suppose say either if I'm producing 1,000 liters of biomass of culture, that is I'm preparing a E. coli culture of 1,000 liters. It is not equivalent to the production of 1,000 liters of protein. That's not the amount of biomass or culture is produced like some, and the amount of protein is like just one third of the amount. If I'm producing 1,000 liters of biomass, only one third of the culture of biomass can be converted into protein because that's how this thing works.
Excuse me, sir.
Yes.
Are you changing your slide, sir?
No.
Okay, sir. Uh,
Okay.
yeah.
Next is what our main goal and what our targets. We ensure that our gene of interest produces desired protein maps or fabs or the vaccine that can be inserted into a suitable host. The host can be very either it can be E. coli, yeast, or a mammalian cells. The mammalian cells either known as CHO, HEK, chikungunya cells. We also ensure that the qualities of cells, we maintain the quality and both quantity of cells can be desired. We maintain the both quality and quantity of cells because either if a cell is damaged, they cannot produce a good quality of products. Uh, Then our goal, we make sure that if our cell is healthy, we inserted that gene of interest into these cells that that is to produce a good amount and good quality of biotherapeutics protein. Throughout the process, throughout the process we ensure that the product yield and the product quality cannot be decreased, even it is small scale or even to the large scale production. The upstream process that I am talking about, the upstream process can be involve a series of steps. Then is media screening, optimize growth condition, induction optimization, cell disruption, process optimization, and last one is bioreactor scale up. Uh, why we are doing this? Because if we don't optimize the media, the different organism needs a different medium to grow. As you studies biology, you know that every organism needs a different environment, different conditions to grow. We optimize those conditions, make sure that these organisms can which are produce our protein may viable or have the activities, the good activity conditions in the good optimum growth conditions. If we don't provide a good condition, the optimum condition, they will be low because they are bacterial cells. They may be adapt to the harsh conditions, but they do not produce a viable or suitable products that we need. And third one is the induction automation. Induction is a phenomenon that we produce, we can grow many bacteria, a large number of bacteria can grow. But can the bacteria produce protein? So either they are increasing their numbers. That's a problem. The bacteria initially starts to grow the number. They divide, make their whole colonies, but they cannot produce protein unless we make them. There's the steps of induction. We make the bacterial cells to provide to produce protein, not increase their numbers. This includes the basic phenomenon of lac opening. If you know about the lac opening, that is the lac promoter gene, and that is the T cell polymerase act on the gene. That's why they promote and they produce mRNA sequence and prolong their produce proteins. And next is if you have a protein, the cell have produces a protein. Either it is inside the cell, outside the cell. We can make that happen while designing the host, whether it have to be protein produced inside the cell or outside the cell. and we making sure that the when we disrupt the cell, when we let's say open the cell envelope, either it is in cytoplasmic fraction, either is in closed fraction, as well as in different bodies. They are packed structure inside a closed envelope. We have to make damage in the envelope to take out a protein. The lastly, process automation. These processes can be changed of many terms. Either you have to make them the media, change the media, change the culture. You have to change the whole process, which is basically act on the um, how would I say that if you take a one bacterial cells, there are various number of bacterial cells in E. coli as well. If I take one strain of E. coli, maybe that will work, maybe that will not work. If it will not work, then we will change the strain of that bacterial cells. That also not work, we will also change the next. The next is bioreactor scale up. The typical bioreactor we are using this append is a microbial bioreactor vessel system designed to support the growth and metabolic activity of a microbial cell host. These are basically purpose designed to produce a biological product which can be ensured that there are no optimized there are various optimized conditions to ensure that our desired product can be produced via priority scale going up to a large scale. These are the basics of the upstream bioprocess. Thank you. If you have any doubt about upstream processes or what kind of biotechnology activities, or if you think about malware practices, you can ask any questions.
Participants, if you have any queries, you can ask sir right now. And I hope you are able to access your mic as well, and you can also put your questions in the chat box.
Good evening, sir. Sir, can you listen? Can you hear me?
Sorry, your audio is not clear.
Sir, now it's. Can you hear me right now?
Can you type your question in chat box?
Okay, okay.
Okay, Subhas, you have a nice question. You asked about midstream processing. Basically, when we make a culture after the harvest process, either we say the starting of a harvest process to the uh, transfer of sample to the downstream processing unit. We elaborate this. You know about cell disruption method, either sonication or homogenization.
Yes, sir. Yes, sir. Yes. Protein separation.
Yes, so not protein separation is like you disrupt the cell and make the protein out of our cell.
To remove intracellular, yes, sir. To
Yes,
get the
yes, yes.
intracellular proteins.
Yes. That's where the midterm processing is, stream processing is here. You have to optimize that process. If you use sonicator, probe sonicator, uh, you often see that we use probe sonicator to reserve the cell. The sample or even the protein can be denatured due to excess heat, maybe some salts of a buffer. Uh, the point I'm saying that the midstream processing is start from the harvest step to the last harvest after the sonications. That's where the midstream processing is used.
Okay, sir. Got it. Yeah.
Okay,
I was having distinction between clearly what it was. Yeah, got it.
okay. Any other questions?
Participants, we still have a few more minutes before we conclude the session. So if you have any queries, you can ask sir right now.
If you're having a network issue, you can type the questions in chat box.
So I think there are no more queries now.
Okay,
If they have any more queries, the Biopractify team will connect them to you. Will that
okay,
be fine, sir?
okay, very fine.
So, as we come to the close of today's session, I would like to extend my heartfelt gratitude to each of you for your attention and engagement. We have had the privilege of hearing from Mr. Mridul Sharma, sir, whose passion for biotechnology and commitment to research at IIT Delhi have truly inspired us today. Mr. Sharma reminded us of the importance of scientific curiosity and the impact that dedicated research can have on our world. His journey is a testament to the value of perseverance and the pursuit of innovation in addressing the challenges of our time. Thank you once again for joining us, sir, today and sharing your valuable insights. And thank you all for joining us. Let's continue to support and celebrate the bright minds shaping our future. Thank you so much, everyone.
Thank you.
Thank you.